Hello there. I'm Tony Weathers, professor of mathematics at Adams State University in beautiful Alamosa, Colorado, and your host for what I call Grizzly Adams Mathematics. You know, it's been said that in theory, there's no difference between theory and practice, but in practice, there is. Well, today on Grizzly Adams Mathematics, we're going to pay tribute to that aphorism by looking at a fun real-world example and investigating how the theory explains why the practice works. In 2011, I purchased this Volkswagen Vanagon Westphalia pop-up camper. Officially known as the Volkswagen Type 2 T3, the one in the picture here is a 1991 model, which is the last year they were offered for sale in the United States, being replaced by the Eurovan the next year. However, they continued being manufactured and sold in South Africa until 2002. To this day, much of the new old stock that can be purchased from Vanagon supply stores comes from South Africa, and here's where our story begins. Among the many aftermarket upgrades on this van are the wheels. These wheels were manufactured for the South African market and can accommodate tires larger than the ones the van came with. Here's a picture of the speedometer from such a camper, and if you look closely, you'll notice there's a number down here at the bottom, the number 805. This refers to the fact that this speedometer was manufactured to be used with tires that roll 805 times per mile. Not every speedometer has such information printed on it, but I took it as a good sign to a mathematician that this one did. As I said, the reason for upgrading to the South African wheels is to use larger tires, which gives improved handling characteristics and better fuel economy. Because of some of the technical requirements of the Vanagon, I went with BF Goodrich AT2 tires. Here you see the specifications on the tires I bought. And here is the source of the problem. Since these tires are larger, they will roll fewer times per mile. If we calculate the ratio 751 to 805, we see that these tires will roll slightly more than 93% as often as the tires the speedometer was designed for. So the reading of the speedometer will be only slightly more than 93% of the vehicle's true speed. For simplicity's sake moving forward, let's just use R equal to 93%. This meant that if I wanted to know my true speed at any time, I needed to do some arithmetic. Let's let S sub D represent the speed displayed on the speedometer, and S sub A the actual speed of the vehicle. Now the displayed speed is only 93% of the actual speed, which we can represent with this equation. And to find the actual speed, we solve as follows. Dividing by a decimal like this in your head is not something easily done while zooming down the highway, so a slightly different technique is used. With the reasoning that the displayed value is 7% too low, most people adjust by adding 7% to the displayed value to get back to the actual value. And here's what that looks like, but it's not quite clear what this is or why this should work. Of course, anyone who has ever had to do this, and there are plenty, can attest to the fact that it does actually seem to work, at least well enough to avoid getting speeding tickets. Once I began having to do this with my van, I got very curious as to precisely why this technique works. Surprisingly, the path to the answer begins with square numbers. Consider what happens when squaring a positive number larger than 1, such as 3. The result is 9, which is larger than what we started with, and this is true for any number larger than 1, such as 2. When we square 1, however, nothing appears to happen, as we end up exactly where we started. However, if we start with a positive number smaller than 1, say 1/4, we see that the square is smaller than the number we started with. And as we get closer and closer to 0, this behavior is exaggerated. Ultimately, what we see is that for small values of x, with small in quotation marks, x squared is approximately 0. I put small in quotation marks because how small is small enough depends on several factors, not the least of which is what is meant by approximately equal to 0. We'll leave this detail alone so as to not get pulled off into the weeds. Well, if x squared is approximately 0, then 1 minus x squared must be about the same as just 1. Using the difference of squares formula to factor the left-hand side, we get this. Now we divide both sides by the quantity 1 minus x and obtain the expression that explains why this technique works. As we observed, this approximation is valid when x is small, so let's go back to my specific example by letting x equal 0.07. Then we have this expression, which, with a little arithmetic, looks like this. So if we take the expression we ended up with and multiply both sides by s sub d, we can now see that the two quantities are indeed approximately the same, the one on the left being the one easy to do in your head, and the one on the right representing the actual speed of the vehicle. For example, when the displayed speed is 60 miles per hour, we can find the actual speed by dividing by 0.93, and we get this number, which we will just call 64.516 miles per hour. Well, multiplying 60 by 1.07 is just adding 0.07 times 60 to the 60 we started with. Think 6 times 7 is 42. We put the decimal in the correct place. We've got 60 plus 4.2, which of course is 64.2. These two numbers are indeed pretty close. How close? Well, if we calculate the percent error, we can see that this approximation is off by less than 1/2 of 1%. That should certainly be close enough to prevent running afoul of the law. Here's a graphical representation of the difference between the two approaches, with the red line being the one corresponding to the division and the blue corresponding to the multiplication. As you can see, it's very difficult to tell them apart. This graph adds in a black line for the displayed speed, which is slightly below, as we already knew. And this graph zooms in on an area containing typical highway speeds, and now we can finally see just a little bit of difference between the red and the blue graphs. Once again, we see that mathematics is the key to happiness. Thank you for watching this video. Check back for more videos from Grizzly Adams Mathematics at a later date.